Hi everyone. Today we're going to have a look at Euler's formula, which is a way of writing complex numbers in what's called exponential form. So Euler's formula is in this rectangle here, and it says that if we have a complex number in polar form, so we know the modulus and we know the argument, we can write it in exponential form. So re to the I theta, where r is your modulus, theta is your argument. So you're basically just taking those two parameters from polar form and writing them in a different place in exponential form. Exponential form makes a lot of our calculations much easier, and it helps us tie what's happening in polar form to our index laws, because we're dealing with indices when we have this power of I theta. And that helps us understand why we're adding arguments when we multiply complex numbers and why we're subtracting arguments when we divide complex numbers. Okay, first example we're going to look at here is simplifying the product of these two complex numbers in polar form. So I've got cis pi on 3 times by cis pi on 4. Not too tricky in polar form, but even quicker in exponential form. So I'll take these two numbers and I'm going to convert them into exponential form just by rewriting it. So that first complex number, cos pi on 3 plus I sine pi on 3, can be rewritten in exponential form as e to the I pi on 3. The modulus is 1, so we don't need to write anything there. Multiplied by second complex number, cos pi on 4 plus I sine pi on 4 is e to the I pi on 4. So I can see now, just using index laws, when I multiply two numbers with the same base, I add the powers, which is why I add the arguments when I multiply two numbers in polar form. So I'm adding my powers and I get e to the I, that will be 7 pi on 12. And if I wanted to write that back in polar form, it would just be cos 7 pi on 12 plus I sine 7 pi on 12. So, nice and easy, just adding our powers together. It also helps us to find powers of complex numbers, because again, these operations are much easier in index form because we already know all our index laws. So here we're going to find z cubed, where z equals 2 cis pi on 3. I'm going to write that in exponential form. So 2e to the I pi on 3. So all I have to do is put my modulus and argument in the right spot. And I'm cubing that number. So I can see that it's going to be 2 cubed, e to the I, and then power of a power, I multiply. So it'll be 3 times pi on 3, which is 3 pi on 3. Then I simplify, 2 cubed is 8, e to the I pi. Now, whenever I get one of my arguments that's on the boundary of a quadrant, so that's 0, pi on 2, pi, and then either 3 pi on 2, or if you're using principal arguments, negative pi on 2, that's where my number is going to be purely real or purely imaginary. So, to simplify this, I could write it as 8 cos pi plus I sine pi. And then I could see that cos pi is -1, so I get -8 sine pi is 0, so there is no imaginary component. Or I can just look at my Argand diagram and see that pi is actually on the real axis to the negative side of 0. So it's going to be -8. So that is a quick look at Euler's formula, which is just converting complex numbers from polar form into exponential form. And you can use the same skills as you would to convert from Cartesian to polar form, to convert from Cartesian to exponential form, just by finding the modulus and finding the argument.